Assignment 2, you should all be working on that steadily now, getting towards the end. Some of you may have a rough time with group work. It's always more of a challenge. When stress levels are higher, it's often harder to work well as a team. One of the most simple rules I can give you by way of advice, having dealt with a few groups who are having difficulties, is make sure expectations are clear. Okay? So it's not much use saying so-and-so did not do X or so-and-so did not do Y unless you had already clearly agreed. And the best way to do this is to write that down, the task.md file in your admin directory. Write down exactly who's supposed to be doing what, so your communications are really clear. Almost all big problems we have in groups come down to communications failure. So the best defense you can have is to do a really good job of communicating and just be as clear as you possibly can. Don't forget academic integrity. It's a major issue. It's a very important factor. If you're an ANU student, one of the things you walk away from at the end of your degree is that you've got a degree at a top institution, at an institution that takes this seriously. That's a badge you can wear with pride. But the consequence of that is we do take academic integrity seriously. And so you'll need to act appropriately and be very well aware of what that means. Okay, schedule. There are no labs this week or next week. There's no scheduled labs. And there's no lecture this Friday, so you get a long weekend from lectures. There are one-to-one consultations, however. They're continuing through the next 2 weeks, right the way through the end of the semester, including week 12. Each week, we've got 9 opportunities for you to have a one-to-one consultation. This is particularly useful for things like if you have a problem with your computer or something that is visual. It's often hard to debug those via Piazza. And your tutor may not have time to spend a lot of time with you one-to-one in your lab where they've got to deal with a whole lot of students. But the one-to-one consultations are perfect for that sort of thing, where you've got something that needs debugging like that or you need help with. And it's also a great opportunity for doing exam revision. One of the things I've recommended to a number of students is if you're feeling like you might be a bit behind, start going through past exams, start going through the mid-semester exam, look at these questions, and when you can't answer a question, try your best, look things up, and if you can't get through it, put it aside, make a note, and then come back to a one-to-one consultation session. There are 9 of them each week, right? So come back to one of those and ask for assistance with the thing you had troubles with there. Okay, you really should make the most of those. They're a great resource, so please make the most of them. And don't forget, you've got student reps. We probably haven't emphasized that as much as normal because of the chaos that ensued from the lockdown. They're on the course website. And when you go to help and you go to peers and tutors or peers and lecturers, at the bottom there, you'll find your student reps and you can reach out to them and contact them. Okay, so please make the most of that. The last thing is for the exam, if you happen to be living somewhere between Halifax in Canada and Kolkata in India, then please contact me. There's a Piazza post about this. Contact me and talk about alternative arrangements for the exam. This is because people in this time zone, in these time zones, that time zone, all the way through to this time zone, would be doing your exam in the dead of night, and so that's not okay. So if you're living between here and here in the world and you'll be there during the exam, please reach out to me on Piazza. Read the Piazza post first. There's a pinned Piazza post about the exam. Read that first and reach out to me. Okay, now at the end of the last lecture, we were doing the ADT, and I hit a bug right at the end. Right at the last moment. I'm just going to go through this again, the tree ADT. I'm going to go through this again, and I'm going to do live debugging. I pushed a fix to the bug, but I think it's best if we do the bug, solve the bug. And some of you probably were impatient. That's why I solved it straight after the lecture, or an hour or two after the lecture. I went and solved it and pushed the solution. But I did that quickly so anyone who wanted to know could see, but it's really best to solve bugs live in the class. And now some people probably think, wow, why is Steve digressing here or not following the script or whatever? This is a very important part of my class and the way I teach. In fact, because I'm doing it via video rather than in the class, we're not doing as much as I normally do. I normally do that a lot more. That is, I try to follow the lecture where you all want it to go. And it's often easier when I can see your faces to see which way you want it to go. But I've tried to do it this semester, and on Friday's lecture, someone had a really good suggestion. It was a great suggestion actually about changing the interface, not changing the interface, but changing the return value from being a pointer to being a Boolean. And I did that, but by doing so, I went way off script, which is cool. But I ran into a bug. Okay, so now let's go through and look at that bug. And before I do, let's just quickly remind ourselves about the trees. A binary search tree, that's not a binary search tree. That's got, this one here's got 3 nodes. A binary search tree has 0, 1, or 2 children per node. Here it is, binary search tree. And we're creating a set. There's a set of fruit there. They're reflected in the tree. Remember, the tree is sorted, and the order and the shape of the tree depends on the order in which the elements were added to the set. And as someone pointed out in the last class, if that set was sorted before we added it, you'd end up everything would get added in order, which would actually give you a terrible result to your tree, because this tree here would end up looking like a linked list, because everything would always go to the left or to the right of the last thing you added, which ends up the binary search tree that looks like a linked list and has all the bad behavior properties of a linked list. So that would be bad. Okay, so that's really worth thinking about that and understanding that statement. The statement was that if the elements of this set were sorted before they got added, then we'd actually get a worst case tree shape. And to get the best case tree shape, we'd have the middle one, and then the middles of the middles, and then the middles, we'd do it like that, like a bisection search. If we put them in exactly that order, we get a beautifully triangular tree, or as close as we can given the number of elements. All right, so now let's go to the code. All right, oops, we're not there yet. Let's go to the code. I'm going to leave this on the screen because one of the issues we have, okay, so one of the things that we ran into was a question of what do we do when we want to delete something? And the first point was, if I wanted to delete a leaf node like this plum here, this peach here, grape, or apricot, those ones are all leaves, meaning they're the only nodes in the tree which don't have any children. Every other node in the tree, unless I missed one, every other node in the tree's got children, okay? So if I delete plum, then all I need to do is to find the parent of plum, which is pear, and put null here, and we're done, okay? But if I was to delete pear, which sits here, it's a bit more tricky because I need to keep peach and I need to keep plum. And the approach was to go to the parent of pear, orange, delete that, so set this guy to null, and then remember this peach and add it back into the tree, and remember plum and add it back into the tree. And that way we've kept everything except, my mouse has blanked the screen. Okay, we've kept everything except the pear, which is the thing in that example I gave that we're trying to delete, okay? So we set this to null, but we remember this one, pop it back into the tree. We remember this one, pop it back into the tree. And the place where the peach and the plum fall will be over here. And in fact, what you're going to end up with, if you think about it, if you put the peach in first, that's the leftmost one in first, it would go in here. Peach comes after apple, so it'd go to the right. Peach comes after orange, so it'd go to the right. There'd be nothing here because this is null. Remember, we've just removed that one. And so peach would sit here. And then we'd add in plum. And so we'd go like this, we'd go like this, and we eventually come to here, and we have peach there, and not pear, and then we'd put plum to the side. So you'd end up with a tree which had peach here, and this would be empty, there would be nothing here. That's what would happen if we delete pear. Okay, so it reshapes the tree. All right, so now let's look at our code. Let's go to the code. Oops, not that, recursion there. Let's go to the code. This is where we were when we left off. So I've backed out of the changes that I committed and pushed to the class repo. So this is where we were when we left off, and we ran into a bug. So let's just look at it. We run the tests like this, and we hit a bug. Okay, assertion failure. So let's debug this together as a class. We go to this thing here, and look what's failed. Okay, let's have a look at this test. This is the remove test, and look what goes on here. We add Alice, and then we've just added Alice. In fact, all we've done is add Alice at this stage. So add Alice. These are tests because to say that Bob and Cindy shouldn't be in there. Of course they shouldn't because we haven't added it. Then we remove these things, and we remove things that don't exist, which also should be okay. You should be able to remove something that doesn't exist. That's all good. And then if we remove Alice, that should have actually taken Alice out of the tree, and we get a size of the tree size 0. That didn't fail, so that was okay. But when we went to check if Alice was in the tree, it said it is in the tree. Okay, so we had a problem. We supposedly removed Alice from the tree, but when we checked afterwards, Alice is still in the tree. So something's not right. What's interesting here is to observe that in this test, at this point, Alice is at the root of the tree because it's the only thing in the tree. So it must be at the root. Okay, so let's go back to our PowerPoint here, our picture. It's like removing this one over here. Okay, if you remove that one, it's a little bit special because what's referring to it, not its parent, but the actual tree itself. So let's have a look at the code. Go back to our code here and see if we can see what's going on here. Tree set, here it is. And so what we've done here, if we wanted to remove Alice, we're going to find Alice. Okay, we find it, and we're getting the parent of Alice. Okay, but the thing is that the parent, right, okay. So the trick is though, if the tree is equal to the parent, if the parent is the tree itself, then we know that it's the root. Okay, so so parent is okay. So what we need to do now is we need to say if the tree is null, if if the tree is equal to, if tree equals a parent, okay, that means we're getting rid of it. I think that's right. Yeah. So, right. So this is, I think that's right. Yep. So we want to say if what we're going to remove is the whole tree, then what we do is instead of pulling that tree out of the whole tree, the parent tree out of the whole tree, what we do instead is this. So we go like this. Now what we're going to do is we're going to say, we'll just make the tree equal to the left and add in the right. We can do that. We can say tree equals L. Remember, L is the one that we remembered coming out to the left. Okay, so so we can make the tree equal to L. The thing is though that the tree itself may be null, but left may be null also, right? So it's possible that there's no left and there's no right. Okay, both of these are possible. Okay, in fact, it's going to be true in the case where we're removing the root of the whole tree. So we're going to say tree is equal to L, and then what we're going to do down here is we need to, in fact, we can move this up here just to make it more neat and get rid of these things. Get rid of this, cleaning things up a little bit here. Okay, so now what we're going to do is we're going to say if, actually what we can do here, we can do it like this. Sorry, I'm just making this up as I go along a little bit, folks. I don't know if this is going to turn out to be the same as what I had in the repo, but we're going to solve this bug together live. Okay, so what I've done now is I've said, well, we're removing the whole of the tree. So we set tree to null. Then we're going to need to add left and right back in. So what we'll do is we'll say if tree equals null, then tree is equal to the left thing. We're going to add left to the tree, but there is no tree. So we're just going to say tree equals left, right? Else tree, we'll add it, okay? And then we can do the corresponding thing here. If tree, it could still be null, of course, because left could be null. Tree equals null, then tree equals right. Otherwise, add right to the tree. Okay, and I've written them in the straight line code there just because I think it's easier to read. I find that easier to read for these very simple statements. Let's see if that has solved our problem. And then I'll run through it again to explain it to you in a second what I've done there. Right, it has. Oddly enough, there's another bug in the code which I want to get rid of, which I think our tests aren't showing up. So we fixed the bug. But what I haven't done here, I think, yeah, here, there's a problem here, and that is that we we've accidentally put tree.right, whereas this code here is in the context of the tree. So this prefix saying tree.right, that's actually wrong. It should be just like this. This is a second bug that I found when I was looking at the code after the lecture. Okay, like this, get rid of that. This is quite important. Interestingly enough, our tests would never have shown up this bug. Can anyone on the chat see why our tests passed even though I had that bug? I just removed a bug here. If anyone in the chat can see, why did the test pass? Question for everyone. Why did the test pass even though I had that bug still there? That's a question for you all. The bug was, and while you're thinking, the bug was that when I wrote this code in the lecture, I wrote tree.right, tree.right, tree.left, and so forth, instead of it just saying right, okay? Because we're within the tree. And don't forget, this is an inner class, so if I say tree.right, it's going to go right the way back to this thing, which means it's always going to refer to the root of the tree. Whereas actually what we wanted it to do was to refer to any given subtree. So I'm telling you now for sure that what we had was wrong, but the test didn't show it was wrong. And I was just thinking now about why it is we got a pass, even though we had that bug in there. Okay, so this should still pass. Yeah, this is still passing, but it's quite different code. And the old code was wrong. Did anyone have any guesses as to why it worked even though it was wrong? The answer, folks, I believe the answer is that our tree never got beyond depth of 2. If it had got a deeper depth, this wouldn't have worked. Okay? So I'll let you think about that more later, but now we've fixed both those bugs and we can move on to the rest of the class. So the main thing I wanted to show was here, we didn't deal with a case where the thing we wanted to remove was actually at the root of the tree. And so I've dealt with that by saying, okay, if we want to remove the thing that's at the root of the tree, we'll have to make the root be null. Okay, tree equals null. Otherwise, we pluck it out of one of the children. Okay, so we just make it equal to null. And then when we go to add the left and right back in, which is what we're going to do, we're going to add left and right back in. If the tree's null, to add it back in, we just make the tree equal to the left. Okay? And so we add, otherwise we add left in, right? Having done that, the tree could still be null because L could be null, right? It's possible that when we did this, that was null. So it's possible for tree still to be null. In which case, when we add R in, we just make the tree equal to R. Otherwise, we add R in recursively using this method we wrote in the lecture here for adding a subtree into a tree. All right, any questions on tree sets or sets? If there aren't, I'm going to move on to our next major topic.
Not yet. So,
okay. Yeah. Well, let's forge ahead, folks. I really want to finish this in today's lecture. It's a really great way to finish the week, this part of the course. Now, I want to emphasize to everyone here and to everyone who's not here, who's watching on the video or was hearing it from a friend, this stuff is incredibly important in the course. Why is it so important? Well, containers are something we covered before the mid-semester break. Now we're understanding how they work. We're building them up. So you really need to understand this stuff, okay? Because it's helping you how to understand containers. I'm showing you a lot more about how to do test-driven development because we're using tests at every step of the way here. And we're showing you we're showing you how to build trees. We're showing you how to use hash maps. We're showing you how hashing works and a whole lot of other things like that. So it's really integrating a whole lot of things we learned through the semester are all coming together now. So if you missed these lectures, this A series, you've missed a giant chunk of the course, okay? So all of the A series of lectures are incredibly important because they integrate so much. And of course, that translates to the exam. You look at the past exams, you'll see that there's plenty of material that plays to the A series. So you really want to understand this stuff, folks. And if you're having troubles, go to the consultation sessions, ask on Piazza, ask your tutor. Lots of opportunities. All right, so now we're going back to maps. Remember, we covered containers way back in J14, I think it was. And we talked about abstract data types, that we had lists, we had sets, we had maps. Now we're going to go and implement a map, okay? So let's recap. List, set, map. We've got an array list, a linked list, a hash set, a binary search tree set, a hash map, and a binary search tree map. Okay, we've got all these things here, and this shows you how they map into these units. And we also introduced hash tables and trees in order to do these things. We use trees and hash tables here, and today we're going to use trees and hash tables here. Okay, what is the map ADT? You should already know this. It goes back to J14 or whenever it was at the end of the Java units. A map consists of key value pairs. Each key may occur only once in a map. What does that remind you of? On the chat, if you can tell us what that reminds you of. The fact that a key may occur only once in a map. What is a key like? How do you talk about the group of keys in a map? Think about that for a moment. It's actually really important, and it becomes really important in a few minutes when we do the coding. Values are retrieved from the map via a key. And remember in the code, I think I'll bring the code up from where is it? Here we go. J14, class list. You may remember we put these things into maps. We put students into maps, okay? We had a list, an array of students, and then we put them into a map. We did a put, and then we did get, and we pulled all the values out of the maps. We pulled the keys out of the maps and so forth. If you've forgotten this stuff, go back to unit J14 and take a look. Okay, values can be modified. So if we've got a key and a value, I can change the value associated with that key, all right? And I can get the value by giving the key, okay? And this thing, the first operation here, to put something into a map, the operation we use is put. To get something out of the map, the operation we use is get, okay? And if you do a put for something that's already there, the side effect will be changing the value you provide. So if you have a key value pair and that key already exists, then your new value will override the old value, okay? This is a simplified interface we're using in our class, which we'll be using today. Notice we've got type parameters here. Instead of the single T here, we've got a KV because we've got a key type and a value type, which may be the same or may be different. You know, it could both be strings, for example. You have a string key and a string value. You could have a string key and an integer value. You could have a student value and a string key, all kinds of possibilities, okay? So the idea is we have these two different types and we express everything in terms of the K type, which is the key type, and the V type, which is the value type. And so when we do a put, it returns, we provide a key and a value. When we do a get, we provide the key and we get back the value. When we do a remove, we provide the key for the thing we want removed from from the map, sorry. Did anyone answer the question? Yeah.
A question from Bradley. He asked, can we implement keys using sets?
Can we implement? Great question.
Dictionary.
Okay, great question. Okay, the question from the chat was, can we implement the group of keys as a set? And that's exactly the answer the question I was trying to provoke. If you're thinking about it, you'll realize that the group of keys in a map is exactly a set. And that's really cool because that means that when we go to implement a map in a minute, we can actually take a lot of the code we used for the set and we can do it both ways. We can do it as a hash set, and the hash map can be based on the hash set, and the binary search tree map can be based on the binary search tree set, because the set of keys is actually a set in the map. The keys of a map form a set. So that's a great question, and the answer is yes, we absolutely can, and we're going to. Right, so this becomes clear here. The relationship between a set and a map becomes clear here. What's this thing here? This is the example we had from a few lectures ago of a hash set. So it's a set of fruit. They're strings in this case, and you can see they're hashed. We've got a very simple hash here which does it alphabetically. We're only in this particular set of fruit, none of them are in this range from U to Z. They're all in these other letter ranges as it happens. And then at each hash bucket we've got a linked list. And this is a data structure we all implemented when we implemented the hash set. And you should be able to remember how we use that. Now, what's the relationship between that and a map? Well, maps have key value pairs. A set just had the elements, so each node just had an element. And for a map, each node has a key. We don't call it an element, we call it a key. That's a key, and that's the value. So in this example here, you can imagine it being the prices, right? So apples are $3.50 a kilo, bananas are $2.50 a kilo, or whatever. And so you've got this node here. This is a key value pair. And you can search for the price of apples by doing a get operation here, and it'll look for apple and it'll return $3.50. You can do a put operation here and say put banana $3, and it will look through here, find banana, and then it will set that value to $3. And if you wanted to do a put of mandarin $7, it would go here, look in here, it wouldn't find mandarin, it would create a new node, and it would say mandarin $7. Okay, so in the case of banana, it was something that already existed, and it would change the value. In the case of mandarin, it was something which didn't exist, and it would add a new key value pair. Okay, so here, let's do it again. That's a set, that's a hash set, that's a hash map. Okay, very, very similar, and I've deliberately drawn it this way, even though actually in Java, this is actually a type called a key value pair. You can see here the relationship between a set and a map. And I'm deliberately, as we go and do the coding exercise, going to copy code from the sets to the maps to make it absolutely clear to everyone the relationship between the implementation of a set and the implementation of a map. And so here we go, we're looking for apricot, we're doing a get operation and we get 550. Okay, just like when we do a contains operation in a set, we can do a get operation in a map and we get back 550 because we get the value that's held in that map. And we do a put operation for grape, $7, and it goes in there and it, hang on, what was that before? Okay, grape wasn't there. So it goes and adds grape and with the value of $7. And now we've got put orange 350 and it changes it from $4 to 350 and so forth. We can do the exact same thing with trees. Okay, that was hash sets. So that was a hash map and a hash set. That was the set. That's the map. Now we've got a tree and we can have the same relationship between a tree set and a binary search tree set and a binary search tree map. And so now every node, instead of just having an element, it's got a key value pair. Okay. Instead of having just an element, it's got a key value pair. And we can do the same operations. When we want to do a get for apricot, we walk through the tree, find apricot and return the value, which is 350. We want to do a put for grape. We go through here and grape wasn't in there, so we created a new node and set the value to 7. We do a put for orange and it was there. It had a value of 4. We changed that to 350. And that's it. All right, so let me start the mini quiz. Where is it? I don't even have Piazza open. And we'll start coding. The first thing we're going to do when we do this coding is write the tests, of course. All right, so there's the mini quiz. It's all there for you. And let me move on to the code. All right, so by the way, first thing I'm going to do is change these tree set. I'm going to change this to BST. I can do that by doing a refactoring here. Refactor, where is it? Refactor, rename. We'll just change it to BST set. It's a little bit more helpful. It's not just a tree, it's a binary search tree. Okay, and that's just slightly more useful. And we'll call this the thing we're going to make here. We'll call it a binary search tree map. All right, so that's our test over there. We're going to copy that test and we're going to paste it in here. Okay, so, and we're going to change the name. It's going to be a map test. All right, map test. And then I've already created, add it. All right, and I've already created the interface here. We'll create 2 new classes here. So we'll say new class, new Java class, and we'll call it hash map. Okay, and it's going to implement, yeah, we'll add it to Git. It's going to implement the map. There we go. All right, so hang on a minute. Let me just check what I'm doing here. Yep. So it's going to implement map like that. Now, one thing we haven't done, we need to do here is we need to put this k, comma, v. So it's type parameterized the same way as map is, with key and the value types, right? They're the types for the key, the type for the value. And then, of course, it's going to invite us to go and fill this in, implement the methods. Yep. So we'll implement this full of empty methods. Okay, so this is our stub for the hash map. And then we'll do the same thing for the BST map, binary search tree map, like that. Add it to Git. We'll write the type parameters in, k, comma, v, and we'll say it implements map, kv, like that, and then we will get it to fill in, implement the methods. All right, so now we have 2 stubs. And we've got a test which isn't really testing what we want because at the moment it's just testing the sets. Okay, we want to change that to test maps. Okay, so we need to do a lot of stuff here to change this. So let's walk through this. Well, hang on a minute. Why did I do this? The reason why I did this is because of the relationship between sets and maps. Therefore, instead of writing all these things from scratch, I'm pinching the code here and we're going to modify that code to make it test maps, and in doing so it should reinforce the relationship between a set, which is where this code came from, and a map, which is what this code is going to become. Okay, so the transition we do now should tell you a lot of what you need to know about sets and maps, okay, and their relationship. So let's start off by changing this because it's not add. What's the operation we use for maps? We don't use add for maps. What is it? Can anyone remember? Write it on the chat if you can. It's put, right? And then do this here, put And then instead of contains, we're going to do a test of get. Okay. And now what I'm going to do, and remove is the same, we've got the same name at least. Let's just do a global change of add to put. And we'll do, where is it? Search. My cat's pestering me. Edit, find and replace. Hang on. Edit, find and replace. I'm trying to do this as fast as we can. I know we don't want to take longer at this than we need to. So wherever it said set.add, we'll do map.put, right? Set.add with map.put. Map.put. Okay, replace all. Bang. Just saved us a bunch of typing. Right? Okay, so map doesn't exist yet. We'll say that map. We'll say map. And we'll say hash map. Map. And what types are we going to do? Let's do, what did let me see. I think I had ages, but I'm not sure if I did integers or did I do strings. Yeah, I did integers. Okay, so for this test, what I'm going to do is I'm going to have the key be the person's name, like Alice and Bob, and the value will be an integer, which is their age. Okay, so we'll make it a string, comma, integer map. That is, the key type will be string, and the value type will be integer. Like that. And change this to a map. Like that. Okay. Now, we still have issues here. Set.size, we're going to change to map.size. Map.size. Like that, replace all. Bang. Okay. So now wherever it said, set to string, we'll change that as well. Set.toString. Will be map.toString. Replace all. Okay. And here we're going to need to replace this piece of code which we just wrote. We're going to do that the same at the top here. And do the same here. And do the same here. All right. And we've still got lots of contains. We've got to fix all those contains. Instead, what we're going to have to do, instead of contains, what do we do? Where it says set.contains, how do we write that? Anyone know? The equivalent of set.contains is set.get in map.get. Okay? .contains, we map.get. Okay? Okay. Now, the other thing we want to do is we want to change all the times where it says map.true, assert true map.get. We actually want to say assert equals map.get, okay? Because we're going to get a value back. We want to see if it's the value we expected. So it's going to be Alice's age. All right, so let's just do that. That'll take a moment. So we say assert true brackets map dot get, which is probably going to be lots of those. We're going to say instead assert equals map dot get, like that, and replace all of them. Okay. And we have to pass values there. And for false, do we have not equals, assert not equals? I think we do, don't we? I've forgotten now. Let's just try that. Assert not equals. Yeah, there we go. We'll do the same thing here. So we'll change all those falses into not equals. Okay, so wherever it said assert true, we're going to change that to assert not equals. Not equals to, assert false is going to turn into a not equals. Any questions there, Leo? No. All right.
No.
All right.
It's really weird, but I didn't get anything.
Yeah, you're surprised, huh? Okay. Now, we've got set.remove. We're going to have to change it to a map.remove. And I think we're just about done with that very simple changes. All right. So set.remove. We'll change it to map.remove. Like that, replace all. There they are. Okay, now let's go through and actually make these things sensible. What we're going to do is to add ages for these people. Okay, so what we're first going to do is we're going to put Alice 19, then put Alice 20. Okay. And now when we do the toString operation, we've got to do this, right? It's going to print. It's going to give us a key value pair, which is going to look like this. Okay. So when we say if we do map.toString, it's going to return. It should return that. Okay. Now map size should be 1, and then it should be this Alice.20, comma 20. Right, that's what we should get now for the map, because we've just changed Alice from 19 to 20. So we put 19 there, now we put 20 there, so it should look like this. Now we're going to put Bob, we'll make Bob 20, and the size should be that, and we should get Alice 20 and Bob 20. They should be the two values, right? Alice, comma 20, Bob, comma 20. Like that. And then over here, it should be Bob, comma Alice, just the alternate ordering. Remember this, because we don't know what order they're going to come in. It's not a guarantee. Like with sets, same with maps, there's no particular ordering to the elements in the map. So we can't be assured of that. Okay, we do the same thing with Bob. Let's change Bob's age, like that. And then we should get basically the same here. I'm going to cut and paste this here. But now Bob's age should be different. So Bob will be 19. 19 now. So we just changed Bob's name, age. It should only be one Bob, but his age should have changed, right? So by doing a put of Bob 19, it's changed it from 20 to 19. There should still only be one Bob, but Bob's got a different age now. Now we'll put in Cindy. And now we put in Cindy. Like that, and that won't affect the size. We're not going to check all the different possible outcomes like that, but the size should still only be 3. Okay, so we added Cindy, the size should be 3, and we've put Cindy, the size should be 3. Okay, it shouldn't change the size because we're just changing the value for Cindy. Okay, now we're going to have this whole thing where we put in nulls. Okay, and so what this is the null is now the key. Remember, it was the element in the sets. Now it's a key. Okay, so now we're going to say null, comma, let me just make sure I'm getting this right here. Yep, we're going to put in something like this. Null can be 1, it can be any number we want, just any integer. And now what we expect to get is this, a key value pair, not just a value, not just an element, but a key value pair, like that. And then we put in null, comma, some other value like that, and we should get the same thing. Now we've changed it, but by doing a put with a different value, we should get it like that, okay? And now we're going to put in Bob, and Bob 20. Oops, I put the comma in the wrong place, like that. And now we should get null, 2. Bob 20, like that, or Bob, again, we don't know the order, so we have to test for both possibilities. 20 and null, comma 2, like that. Okay, and then just cut and paste this to save me retyping all that stuff. We'll make Bob 21 now. And then,
Steve,
yep.
A question from Hoy.
Yep.
She asked, what's the advantage of using assert true and assert equals, and why you change them? Why you have to change them?
Yeah, great question. So the question was, why did I make the difference between assert true and assert equals? Now this is something that I think is better with JUnit 5, but basically that's an irrelevant comment. But equals, the nice thing about equals is that it has this notion of, as you can see here in the gray, see that it says expected? So it's got a notion of what's expected and what's given. Okay, so that's the expected thing. We expect to get 0, and that's what we got. Then when the error message comes, you'll say, we expected 0, but we got whatever you got, right? And it just makes it easier for the user to understand, okay? If I just put a Boolean there, if I just said assert true map size equals 0, then what would happen in the error message, it would just say it wasn't true. It wouldn't tell you that, hey, I expected 0 and you gave me 3. It would just say false, right? I expect true and you gave me false. Okay, so it gives more information to the person using the test. So that's the reason for using assert true rather than, assert equal rather than assert true. So basically use the most specific assertion you can, just because it provides more information to the user of your test, okay, which is often you. So it's a good idea. All right, so now let's do get. We're going to do the same thing here. This is a little bit tedious, I know, sorry folks. So now we expect Alice 19 like this, like that, and then do a get. Now what we expect is we expect 19, right? So we expect the value of, when we do a get of Alice, to return 19, because we just stored 19 up here. We did a put here of 19, so when we do a get, we expect to get 19 back. If it's not, it's wrong, okay? Oh, actually what we can do here is assert equals. I think what we get here is null. Oh, I'm doing it wrong. I think this is right. Oh, assert null, that's what we should do, like that. And I've forgotten if this is even correct. I think that when we do a get, that should return null if it's not found. Let's assume I'm correct on that. Someone can check and tell me if I'm wrong. But I think that's what we do, is the get operation, if the element's not found, it should return null. Now we're going to add Alice at 20, like that. And then the size should still be 1. We should see this. We're expecting Alice, comma 20, like that. And then equals, when we do a get, we should be getting 20 when we do the get. And then for both Cindy and Bob, it should be null when you do a get, because they're not in the map, so you should get null. Now if we do a put of Bob at 21, or whatever, it doesn't really matter what it is, you should do, let's just pinch this code because this is becoming very tedious. Let's just pinch that code there. Where were we? Down here, like that. Was Alice 20? Alice was 20. Okay, cool. Then we say we expect Alice to be 20, like that. We expect Bob to be 20, like that. And we expect Cindy to be null, assert null, because Cindy's not in the map, so we should get null when we do a get of Cindy. All right, now we're going to change Bob to 21, and the size should still be that, and this should be the same, except all the Bobs should be 21. In fact, all this stuff here will be the same, except we'll change Bob to 21. Where is it? Bob is 21, Bob is 21, and change that to 21. And we still expect Cindy to be null, because we didn't put Cindy in there. Now we're going to put Cindy in there and give Cindy some age. And now there should be 3 in there. And we should be able to get, what is it? Alice is 20. Bob is 21. And Cindy is 30. Okay. And then we're going to change Cindy's age. And then we expect 20, 21, and 37. Okay, so, and then we're going to do removal, and then we're finally finished. Phew. Okay, so I think we can, all right, put Alice 19, and we expect Alice 19 to be the string, and we expect our get to give us 19. Whoops. And we expect Bob to be null and Cindy to be null. Okay. And then if we remove all of them, oops, So when we remove Alice, that should be fine. These ones here should do nothing because they're removing something is in there. The map size should now be 0, and we should get a null for all of these. Assert null. Null. Cut and paste. Cut and paste. Cut and paste. All right, now we're going to put these ones in here. We'll make her 20. Oops, whatever. And 22. And that should only go in once, right? Because we're testing for duplicates. And we should see Alice 22 in there. Okay, like that. And then when we do a get, we should get 22. And we should get null for the others. We should get null for the others. Okay, and then we're going to put Bob in finally. Alice 20, what was Alice 22 and Bob 21. 21 like that. And over here we've got Bob the other way around. Okay, so it's Bob going to be 21. Yep.
Hey Steve, here's a suggestion from Yuchen. The students say, should we test to remove from the empty map since we have already learned error handling?
We should. That's a great idea. I'm not going to do that right now, but if I remember, I'll do it at the end of class. Okay, that's a really good suggestion. And in fact, we should be adding more error handling in here. Okay, we can also do things like, what else generates an error? But certainly if we, wait a sec. No, I think that it's not actually an error to remove from the empty one. I don't think that's an error. You can check that. Maybe someone can check while I'm working. Someone can check. I don't think it's an error to remove from an empty map. That's not an error. It'll just do nothing. Okay. So that isn't an error. But if you can think of other errors, it's a good point though. The point was, should we check for error handling? And the answer is yes, we should be. But removing from an empty map is not an error. It just does nothing. Okay. So you can check to see if I'm wrong, but I believe that's right. I should be right because I often make mistakes, so I might not be right. So please go ahead and check. And if I'm wrong, please let me know. But more importantly, more valuably, the point that the student made is a really good one. And that is, if there are cases here where we have errors, we should check for them. Okay, now where am I? I'm going to remove Alice now, and we should only have certain null for Alice, because Alice is gone from the map. And then we do an equals for Bob. What was Bob? Bob was 21. And then a null for Cindy, because Cindy's not in the map either. All right, we're nearly there, folks. Really close to finishing this whole thing. And we're going to put Alice 22. And we get 22. We get 21. And we get null for, oops, that's a comma. And we get null for Cindy. Oops, what's happened here? My computer's stuck. Okay, like that, null for Cindy. And we put in another age for Bob. And we should get 22 for Alice, 23 for Bob. I'm just making these numbers up here, trying to make them different, and null for Cindy. Okay, and then finally Alice is 22. Now some of you might think, wow, couldn't you automate all this? Instead of writing all these things by hand, couldn't we just automate all this stuff? And the answer is absolutely we can. Not in this class though, it's a really, really interesting topic. It's called fuzzing, fuzz testing or fuzzing. And that's actually some of my colleagues, I do a little bit of research on fuzzing as well, but it's a really important research topic, and that is automatic test generation. So Alice should be 22, Bob should be 23, and Cindy should still be null. And finally we're going to add Cindy in and put Cindy, and we do Alice 22, Bob is 23, and Cindy is 33. And we're going to change Cindy to a different value. And then, and 23.
Hey Steve,
yep.
I think student just pointed out in line 142, you miss a comma between 23 and Bob.
Oh, excellent. Thank you, folks. Well spotted. All right, great. Now we've done this and we want to start testing the hash. Map hash, then do a hash map, and we're going to say hash true, and we'll test our hash map and we'll run it and it should fail. Run that test. Oh no, I didn't. I just tested the set. I didn't do, sorry, I did the wrong thing there. This is a mistake we often, well, what happened there?
Also line 124.
Hang on a second. Hash map.java cannot find symbol class map. Why can't it find map? Why cannot find map? All right, what's going on here, folks? We have a problem. Implements map, it should be fine. It could find it before. This is a little bit like the problem we had in class before. Where was the other error, by the way? Can you tell me where that other error was?
Line 124 between Alice and 22. Oh, sorry, and 20. Or 22, I forgot the
1, 2, 4.
Yeah, 124.
Oh, here. Yep, well spotted. Thank you, folks. All right, now we've got a problem. You can't find the class. We had a very similar problem in a lecture before, and in the end, what I ended up doing was just restarting, right? It says cannot find symbol class map. It's right there, folks. It's right there. Why can't it find that? It's right there. Man. Oh, IntelliJ. Close all these things here. In fact, what I might do is just see if I can get away with closing the file and reopening the file. Maybe that will make it happier. If this doesn't work, I'm just going to restart IntelliJ. Map test, run. If anyone can see something I've done wrong, let me know. But at the moment, I think it's just an IntelliJ bug like we had a few weeks ago. Yeah, that's really strange. Okay, hopefully everyone can see that. It says that it cannot find the symbol map. Right, but the map is an interface. It's right here. I don't think there's anything wrong with what I've written here. I'll go to my notes and check to see what I wrote in my notes. Public class hash map implements map. No, I don't think there's anything wrong with it. I'm just going to quit IntelliJ. Yep.
Steve, last time I think we solved the problem by creating a new directory and move everything there.
Oh, that's right. You're right. Okay. You're right. We did, didn't we? Let's just see if this works first. To restart. I did both, I think, but I think you're right. I think we did a. Thank you for reminding me. You can see how slow it is on my machine. We finally finished the unpleasant part. I was going to say this will be fun. We're actually going to get to implement this thing, and of course it misbehaves right on cue. Okay, close. All right, now let's see if we can run the map test. It's still, maybe I shouldn't have been so impatient. Let it finish doing its job. It's still doing stuff, in case you're wondering. I don't know if you can see that on the screen, but it's still busy waking up. If this doesn't work, then we'll do exactly what Leo said, which is what we did in the last class, which was just write the code again. Oh, it worked. There you go. A bit of computer science for you. I just quit IntelliJ and started it all over and everything worked. Boy, that's frustrating. That's really unimpressive, IntelliJ. Okay, no worries. Let's forge ahead. What are we going to do here? Remember, let's go back to the slide. This is the fun part. This is the interesting part of the lecture. Okay, yeah, we're making this transition. We're going from a set to a map, right? This is a map. It's got a key value pair, and that's a set. Okay, it's just got a set of elements. Instead of having elements hang off each node, we've got a key value pair hang off each node. So what do you think the first thing we should do is? If we've got a key value pair instead of an element, we no longer have an element type. So what should we do? I'm going to suggest the first thing we should do is create ourselves a little type called a KV pair, okay? And then we can basically make the data structure in terms of KV pairs, all right? So let's do that. We'll make an inner class here, class KV pair, and it's going to have two things in it. What's it going to have? It's going to have a key of type K and a value of type V, like that, okay? And then we want a constructor. And just simply initialize it as this dot key equals key, and this dot value equals value. All right, and then, importantly, we want a toString method, right? The reason why we want a toString method is we want to do that little thing with a parentheses with a key, comma, value, like that, okay? So we'll do that. We'll say public string, toString, and then what we're going to do is just return the key like this. Okay, so we've now got a toString method, and we've got a very simple little class there called the key value pair. All right, remember our hash map. How do we implement the hash map? Well, we had a table of some size, and the table was a table of linked lists to linked lists of elements, and in our case, linked lists of key value pairs. Okay, so a table of linked lists of key value pairs is what we want. All right, so let's write some code for that. Now, the first thing is, how many buckets should we have? Remember, we call these things buckets. How many buckets should we have? Does anyone have a suggestion? Anyone got a suggestion there?
No, not yet.
Not yet? Okay. All right, we'll start off with an empty table, and we'll
Well, we got several. First is we can use number of keys, and another one from Ethan is we can start from 1.
Yep. Let's not make it 1, because 1 is so simple that there's only one linked list. But if we make it 2, that's almost as small as 1. Okay, why did they say 1? I think that's a great suggestion. I think the reason what motivated that is that if you make it a small number, then that tests things a lot, right? So it's a good idea. If we made a really big number, like if we made 2,000, then actually everything would fall into a separate linked list. Okay, so it's often a good idea when we're testing to make this really small. But 1 may be too small, because that means there's only going to be one linked list, so you don't actually get to use your hash function, because it's always going to go to the same bucket. So so we're going to make it bigger later. All right, and then we need to know how many elements are in our map. Okay, let's go to the hash set here. Hash set, hash set, not BST set. Now, we need a hash function like this, okay? So, and we need a constructor. So let's just copy those two things over. We need a constructor, we need a, let's just dump them in there. We're going to have to modify them. Now, we're going to hash on, what are we going to hash on? Does anyone know what we're going to hash on? We're going to hash on a KV pair, or what? What are we going to hash on? I want you to think about that while I change this code here. It's going to be a hash map. Think about that. What is it? What are we going? What's this going to be? Any suggestions there? I'm going to suggest we want to hash on the key.
Yeah. Actually, Howard just said we can use key.
Oh, great. Okay. All right. So now we're going to hash on the key, and we've got ourselves a KV pair type. So let's go and do the put, right? So I think we're, there's something really interesting, okay? Now, we'll come to it in a sec. Let's just do this put. Something interesting about the, let's do the put, the equivalent of put is an add, right? So let's just do this. Let's cut and paste this. And we may run into some interesting issues as we do this. Let's just start off by dumping this in, because I'm trying on purpose to show you the relationship between the set, which is where I just took this code from, and the map, which is what we really want to do. Okay, so let's just do this. First of all, what are we going to hash on? And someone just said it on the chat, we're going to hash on the key, okay? Because the key is the thing that forms the set, all right? Now, what we want to do is, once we've done that, we're going to get ourselves a linked list of KV pairs, not a linked list of that, KV pair, linked list of KV pair. So that will give us the an entry into the table. Okay, so we've got this, and then that's this hash function here. Okay, so we just took this code here. Actually, what have I done? Hash key, return key. Otherwise, okay, yeah, it's going to return the index into the table. Terrific. Okay, and now what we're going to do here is, if we got back an empty linked list, well, then we know that there's no linked list. This is really, really simple. We just need to create a new linked list, and then we call this new variable we've got up here, we make it equal to the thing we just created. Otherwise, if there is a linked list, sorry, not otherwise, this is not an else. This is just, once we've done all that, we definitely have a linked list there, then what we need to do is, wait a second. Oh, this is a put. I was going to say, if this is a get, we don't need to create a new linked list. But what we need to do now is find out if the linked list already has the element that we want, right? So if it has the element that we want, then we're just going to change the value, okay? But how do I do that? Because look here, this says contains element. So we say contains key, for example. Is that going to work? Would that work? This isn't going to work, folks. The reason why this isn't going to work is because this is not a linked list of keys. It's a linked list of key value pairs. So what we're going to do now is we're going to write ourselves a special little helper method here called find, which is going to find the key value pair in the linked list that has the right key, or return null if there's not one. Okay, so we'll say KV pair find, and then we'll give it a linked list of key value pairs. And what we're going to search for, that's the linked list. LL stands for linked list. And then what we're going to search for is the key, like this. Okay? So we're going to look through that linked list for the key and then return the key value pair which has that key, if it exists. Okay, so how do we do that? Well, that's pretty simple. We just need to loop through the linked list and look for that key for a key value pair. So what we'll do here is to say for key value pair, KV, in the linked list. So we're going to go through all the key value pairs in the linked list. What have I done wrong here? Key value pair KV in, what's happened here? For KV pair KV in linked list. Why is it putting squiggly lines here? Maybe it's just I haven't finished writing this. Okay, so we're going to say if, what does the matter here? Oh, so it's a for statement. Yeah, it's a for statement. That's the problem. My goodness. Okay, how silly is that? I wrote if instead of for. Okay, so for each key value pair in the linked list, you're going to say if the key, okay, if the key of that key value pair equals the one we're looking for, and we're going to use the equals operator, not the double equal sign, because they just need to have the same value. They don't need to be the exact same one, okay? So we're going to say like that. If that's true, then we'll return the KV. We found it, okay? Now, there's one exception here, and that is if we're searching for null and the key is null, then we also do this, right? Because otherwise, what happens if we're searching for null, right? If we're searching for null, then this key could be null, okay? We can't call the equal sign on this, okay? So we say if if key equals null and KV dot key equals null, or if that's true, then we're good. Then we can return the KV. So what that's going to do, otherwise we return null. Because if we got down to here, we didn't find it. Okay, now there's one thing not quite right with this, I think. I think I also need to check the case if here.
Hi, Steve. Sorry to interrupt.
Yep.
There's a question from Hoa. She asked, what if there are more than one entry or values associated with the same key?
What if there's more than one entry which has the same key? That's not possible. It's one of the rules, okay? One of the rules of a map and a set is that there are no duplicates, okay? It's a very important property. Great question, okay? So it means that in the linked list, it's always the first one that matches will be the one that we want because there can not be any duplicates. So the first one must be the right one, okay? I hope that makes sense. So now what we're going to do, now we've got ourselves a little find method because this wasn't going to work, right? Okay, so now what we're going to do is going to do this find method and say if we found something, right? If find ll comma key, right? If that thing is not equal to null, then well actually we need to save it, right? So we're gonna say that guy. Yeah, we need to do it this way. It's a bit nicer. KV pair KV equals find. So we're going to try and find this thing. Okay, so we're going to look in the linked list that we got and see if we can find a key value pair which has the key we're looking for, and we return it if it does. Okay. Now, if we found something, then so there's two possibilities, right? When we're doing a put. One is that the key was already in there, in which case we change the value. Or the key wasn't in there, in which case we create a new key value pair and add it. Okay? So if it's in there, if KV equals null, not equal to null, then we're just going to say KV.value equals value. Okay? So we're just going to change it.
Hi, Steve.
Yep.
Here's a suggestion from Michael.
Mm-hmm.
I think that's for line 31. He suggested we can use object.equals kv.key and key so that there is no dependence on one of them not being null. So you can just
okay. Let's just hear that again.
So
can you say it again?
Instead of telling if key or kv.key is null, we can use object.equals and then kv.key and key to compare these two.
Oh, because it will deal with the null possibility?
Yeah, so there's no dependence on one of them not being null.
Right, I think so. Like this? Can we do this? No, wait. What are we going to call the equals on?
So the kv.key and the key. So that two values. to compare that two values.
The problem is that we can't call equals on a null value. So if this is null, we can't call equals on key, and if this is null, we can't call equals on kv.key. So we can't call equals on a null value. That's the problem.
I think Michael just suggested that method will deal with. Oh, all right, yeah. Michael just said he might be thinking of something else.
Okay, no worries. It's fine. It's good to ask these questions, guys, folks, people. Good question. All right. Hopefully everyone followed that. There was a question about whether or not. So when I wrote this code originally, I just wrote this. This is what I started off with. But the problem with that is. Right, it's possible for either of them to be null. Okay, so that's why we don't do it that way. Hopefully that makes sense to people. All right, so let's go down here. Now, if we got a if we found a key value pair that matched our key, then that means great, we can just update the value. So we're just doing that. Otherwise, we need to create one. So then we'll say, basically like this, we'll say kv equals new kv pair key comma value, right? So we're creating a new key value pair, and we'll just add it to the linked list, and we update the number of elements. Okay. Now, if we do get, let's write get. We've got size here. We return the number of elements. That's easy. Elements, and I think I'm not sure if we're going to pass a test yet. It may be better to implement get first. Let's see if we can do this just with, I forgot the dependencies of the test. Let's see how we go here. Well, put failed. Let's have a look at why put failed. Put should have passed by now, but it didn't. So why didn't it work? Okay, ooh, that's ugly. Our toString method is broken. It printed out that. That's disgusting, instead of printing out that. Okay, that's because we didn't write the toString method. That's easy to fix. So let's go down here. Again, we're going to be lazy and pinch it from here, pinch the code from here. And we'll just say, where's its toString method? Here it is. It's quite a lot of code. We're just going to pinch that whole chunk of code there and put that in here in our hash map. And there's our toString method. Okay, let's look at it. We'll carefully check this code. Start off with nothing. We're going to go through all the buckets in our table. Then we've got a linked list of key value pairs, kv pair, right? And then if it's not equal to null, if it's equal to null, there's nothing to be done. But if it's not equal to null, then for each kv, kv pair. For each kv pair, kv, we'll call it kv. It's not an element, it's a kv in the linked list. If there's something there, okay, this is about whether or not we're going to add a comma. This is all the fancy stuff to make the list look nice. Now, if the kv is not equal to null, we don't need to do this because the kv will never be null. It may have a null key, but the kv won't be null. So we just say, I think we just do this. We just say RT equals RT plus KV, I think that's all we need to do here. Like that. Oops, KV. Oh, well, hang on. Where'd that prefix go? Yep, prefix plus KV. Like that. Does that work? Let's just see how that goes. With a bit of luck, we've got this working. I'm a little bit behind here. I need to hurry up. Come on, computer. All right, yeah, hey, we got the put working, but not the put null. Why did the put null not work? All right, so let's see what happened here. Oh, no, I don't want to see that. I can see the difference between true and false. All right, here, it failed here. It equals that. Oh, haha, we forgot to put the commas in here. All right, so I forgot to put commas in there, which may be the reason, or there could be a different bug, but I didn't put commas in the test, which I should have done. So let's just see. Oops, I didn't put a space in there. It's going to fail here. Yeah, let's put that space in there. That's a mistake. Let's just run it again. Oh, there's something else failed down here anyway, but let's just have a look here. Run this test again. Yep.
Student suggested line 50 doesn't have a space, so you missed it.
Yeah, I just fixed that. All right, we've got a different error now. Oh no, put null worked. Okay, so I fixed the error in line 50 already. I saw the same bug. So put and put null are good. Now we've got a failure in get. That's cool because we haven't implemented get, so we're not expecting it to work. So let's go to our hash set, look at how we implemented get, and get's pretty easy. Add, remove, contains. It's just like the contains, right? So get is analogous to contains. Hopefully by watching this you're getting a sense of the relationship between these different methods. Okay, so now we're going to do a get on a key, and that's a bit like a contains on an element. So we're going to hash on the key. All right, and we're going to get a linked list of KV pairs for that bucket. And now if the linked list is equal to null, that means this key is nowhere. So then we return null. We don't return false, we return null. And then otherwise, I see the find. Okay, so then let's just go and do KV pair, KV. We use our find method we wrote up there a little earlier, equals find LL, comma key. So it's going to go and look inside that LL and see if there's something there. Now, if KV is null, then it means we didn't find it. So we just return null. Otherwise, we return whatever value we found at that key. Else, return kv.value. There it is. Okay, let's see if that works. Run this. And then finally, we're going to do the remove, if this works. Fantastic, that worked. So let's get on with the remove, and then we can move on to our tree. Okay, so here we go. There's a remove. Copy that code into the map. And if you have any questions on the map, let me know. So we're going to hash on the key. We're going to do the same thing here. It's going to be a list of key value pairs. And then we want to say if it's not equal to null. If it's equal to null, then there's nothing to be done. So otherwise, if there was a linked list, then we go and find the key value pair that's relevant. Equals find LL, comma key. All right, that's our little find helper. If it found nothing, then there's nothing to be done because it means we didn't need to remove anything. So we say if KV equals null, then return. Oh, I can do it the other way around just to make it all kind of a little bit neat. We can just go like this. If it's not equal to null, then we're going to remove the key value pair we just found because it's not null. It means it's got the key that we wanted to remove. So we're going to remove that key value pair and we reduce number of elements by 1. Okay, so now let's run the test. Oop, didn't work. What happened? Expected and actual. Let's have a look here. So expected 33, but we got 34. Why? For Cindy, it should have been 34. We put 34 into Cindy, but we checked here for 33. That's a mistake in the test. So let's run the test again. The very last line of the test it failed on. Let's run this again. Fantastic, folks. We've just implemented a hash map, a very, very important data structure. We've implemented it by borrowing from our binary search tree set. We've made our hash set. We've borrowed from our hash set and we've made a hash map. And in the process, you've learned a bit more about testing. You've learned about the relationship between sets and maps. Okay. Now we're going to go to the tree and do the same thing with the tree. Okay. Now, hopefully we can do this faster. What we're going to do the same thing here. We're going to pinch this key value pair. We've got the same concept going on. So our tree, instead of holding elements, our tree is going to hold KV pairs. So let's go here. Where is our tree? BST map. And we're going to paste this guy in here. All right, like that. Okay. So now we've got a key value pair because our tree is our map is going to be a tree of key value pairs. Let's go and look at what we've got for our in our BST set. What's the first thing we do here? We've got a tree and we've got elements, okay? And we've got this whole tree structure here. Remember, this is an internal class, an inner class. Let's do this whole inner class thing here. like that, and grab the entire tree. Okay, that is the tree that we use for storing the elements. We're going to use the same sort of tree to store our, there it is. We're going to use the same sort of tree to store our, there it is, to store our key value pairs. Okay, so now let's have a look here. What's going to be in the, what are the main things that are going to be at every point on that key value, on that tree? Let's go through here. Okay, that was the set tree, the binary search tree set. This is the map. Notice that every node here, now instead of having an element, it's now got a key value pair. Okay, so instead of having an element like Apple, it's got a key value pair like key is Apple, value is 350. All right, so now we've got to change this tree so the tree holds a key value pair. Key value pair is the element. It's going to be, we call it KV, like that. And we'll get rid of this. We don't need to put that prefix in there. Let's just walk through this code quickly and make sure it's making sense. BS tree, there we go. It just took a moment there to get happy. And we're going to initialize it with a key value pair. Oh man, not that one, this one. Okay, and it's a KV. And we're going to call this .kv, KV. All right, there's our constructor. Okay, now for the tree, what we're going to do is we're going to add a key value pair. Okay, we're not going to add a key, so we're going to retain that add function. Okay, just like we did before, but now we're adding a key value pair instead of an element. Okay, so let's do that. So we've got here a key value pair, and we're going to add the KV, and then we're going to say if this is equal to null. That we don't need that anymore because we're not going to add null key value pairs to our tree. Okay, we can add null keys, but not null key value pairs. So we don't even need this anymore. So we can get rid of this stuff. Okay. If the element already exists, then do the following, okay? So, all right. If the key value pair equals this dot key value, that means we actually found the key value that we're looking for. Now, I'm not sure if that's what we want. It's interesting because the way I've coded this up. No, that's right. Okay. Okay, so return false if it already exists. Now let's look here. Else if this dot element equals null and blah 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 blah. All right. So what we're looking for here is deciding which way. So this is a key value dot hashcode and key value dot hashcode. Where do we put it in the tree? Okay, and again, we don't have to worry about the key values being null because we're not dropping null key values in there. We may drop key values which have a null key, but not null key values. Okay, so that makes that code simpler. Okay, now if the right is null, we're going to put this thing on the right if it's greater than. So if the right is null, then we need to create a new one with this key value. So we do it recursively. We just create a new one and we return true. Otherwise, we add it to the right. Okay, so if it's null, we create a tree and we're done. If it's not null, then we add it. Okay, and then the same over here. We're going to say otherwise we're going to go on to the left, and if there's nothing already there, then we add this KV. Otherwise, we add it to the left tree. Now, this is when we add a subtree. If we add this, we want to add one of these subtrees in. If the subtree is not equal to null, then add subtree.kv, we add that kv and we add the left and we add the right. All right, now this is interesting. This is find. So with the find, I think what we want to do is search not for a key value pair, but to find a key value. Okay, so we're going to return a BS tree, but we're going to look for the key, not the key value pair. This is where it's a little bit subtle and a little bit interesting. Okay, so we're going to say k, and it will be key, and here what we can do, what we can find here is that the key we want. So we want to return the key. Okay, so what we're doing here, we're going to look through the tree until we find the one we want. And this is the case where we found the one we want. Now, what we're doing in this code is looking for the element, but in fact, what we want to look at is the key of the key value pair. Okay, so let's just change this. So it's going to be this.kv.key equals key. Hopefully that makes sense to you, that little part there, and I'll go back and fix this code up. So that's the case there where we come to a point in the tree, we look at our KV, we look at its key, and we say, oh, it's the same as the key we're looking for. We're good. Okay, but the other case is if we're looking for if the key we're looking for is null, and this.kv.key equals null, then we've also found the correct one. Okay, so this code here is dealing with a case where the key is equal to null because we can't call key.equals if this guy is null. Okay, so if these are true, then we found the one we're looking for. Otherwise, if the key is null or the key.hashcode, aha. So this is interesting. So notice here that this.kv.cachecode, I've made a mistake here, not here, but up there. Okay, so we're traversing the tree based on the hash code of the key. That's what this code here is doing, okay? And I'll just finish this code off. Okay, but notice that when I wrote this code above, I didn't do that, so that's a mistake. Okay, here, I've done this. And now I've also got to take care of the case where the key is null. So what was that? I treat a null key, if the key is null, right? We treat it as being greater than, okay? Where is it? Here. If kv.key equals null, or that, we go to the right. Otherwise, we go to the left, okay? So we treat it that way. Okay. I think that's right. Let's go back and look at the binary search tree set, see if I haven't messed that code up. Right. If the element's not equal to null, yeah, what I've done is not quite right yet. Okay, so hang on a minute. Let's just think this through. So we've got to deal with the case where the key that we're given, we're adding this key value pair and its key is null, which is possible. Then we need to sort it to the right, so we treat it that way. But the other possibility is where the key that we've landed at, that is the key value pair, this.key value pair is null, in which case we go the other way. So we'll say, I think this is right, so we're going to say this.kv.key equals null. Then we want to go in the other direction, so it's not equal to null. And okay, so what I've done there is I've written a condition under which we go to the right in the tree. We're going to go to the right in the tree. If the node we're at has a null key, then we keep searching to the right. Or if the key we're looking for is null, we search to the right. Okay? Sorry, if the node we're at has a null key, we go to the left. So we don't go to the right if the node we're at has got a null. That's what the not equal sign is telling us. Okay, so now we're ready to do the remove. So we're going to try and remove this node from the tree. And if the one on the right is null, then we found it and we're done. Left is null. Okay, that looks okay to me so far. All right, we've got a toString thing here. Okay, so we're going to do this toString. Our element, let's call it KV. If the KV, no, the KV can't be null, so we don't have to worry about that. So it's just going to be, we can just get rid of all the stuff here. It's just going to be the KV, like when we did the toString for the other one. So it's just going to be KV, like that. Okay. I think we're good then. I think we've just implemented all that tree stuff. We just changed the way the tree works. Instead of working with elements, it's working with key value pairs. And now what we're going to do is we're going to jump to the put and remove and get. So let's start off, oh, hang on, size, we're going to return elements. Oh, we've also got to do the toString down the bottom. Remember, we got burned by that before. So let's look at the set here, see how we did the toString down here. Very simple actually, wasn't it? Okay, so we copy that and put that in the BST map. Okay, there it is. And so what it says is, if we've got a null tree, then just return nothing. Otherwise, we just use the toString method of the tree, which is the stuff we were looking at just a few minutes ago, which is here, which is a recursive tree walk. Okay, so now let's look at, oops, wrong one. Now let's look at the add method, which is the moral equivalent of a put. Remember, it's not the same because here you're just adding an element with a put. We've got to check if the thing's there, and if it's not there, then we've got to where is it? BST map. There it is. So the put and add are analogous, right? But what we're going to do now is we're going to say, first of all, if the easy case is if the tree is null, then it's very simple, right? We just say new key value pair, key and value. That stays the same. Okay, so if we happen to want to put something into an empty tree, well, it's simple. We just add that in. Otherwise, we try and add this. What we really want to do, I think, is we want to go and see if our thing is in the tree by using the find method. And if it is, then we need to update it, right? That's what we want to do. Else, okay, so let's just write this code here. What we're going to do now is going to say key value pair, oops, hang on. Key value pair equals tree dot find key, KV, okay? So what this is going to do, it says, okay, we've got a tree which is non-null. Why did that fail? Oh, it's going to return a BS tree. Okay, now that will return two possible things. It will return null if it could not find the key, which becomes easy, right? And so if the parent equals null, that means it couldn't find it. So we just need to create a new node and add it to the tree and increment the elements. So we'll say just like this. Okay. We can probably write this code more simply. Okay, we can write this code more simply because notice that code there is almost exactly the same as that code there. Okay. Now what we can do is oh no, we don't want to do that. That's wrong. Okay, so we want to create our new sorry folks. What we want to do is we want to add it. We want to say tree.add. Right? We just create a new key value pair with our key and our value, and we add it to the tree. Okay, so we're going to add it to the tree, which will put this in the tree. Right? But we first check to see if it wasn't already in there. Okay. Now, if the thing actually existed, then what we need to do now is we need to update the value, right? So if we looked at key value pair and we found that there was a node there which had that key, which is what this is going to tell us. And then here it's no. Otherwise, yes. Now what we do is we say parent dot kv dot value equals value. Okay, why? Because what happened here is we looked to see in the tree if there was a key value pair which held that key. And the answer in this case is yes, there was one. And it's held by the node parent. So we go to the key value pair and then we update the value according to whatever we're putting here, because that's what put is supposed to do. All right. Now, I don't know how many mistakes we made in all that coding, but if we did that right, we should now be able to pass the put test. Let's see what happens. Oh, we need to go and change the map test. I should have done this before. Change this to test for the tree. Let's see what happens here. So in theory, we're going to get the put test passed, but there's plenty that could have gone wrong there. Oh, we did get put. Okay, we got the put test passed, which is fantastic. We didn't get put null, which we should have. So let's find out why where we went wrong. Okay, so now it says here we went wrong here because we're trying to find a key. It says here cannot invoke object equals object because this.kv key is null. This.kv key is null. Oh, okay, all right. I need to do the opposite here and say that this.kv key not equal to null. Okay, so let me just explain this. I'm just kind of jumping ahead of you maybe. All right, so let's look here. What this tells us is that we've got a problem here because this thing here turned out to be null. It was a null key here. So when I try to call the equals method, boom, it blew up, and now we have this error, null pointer exception. Okay, so it turns out the key is not equal to null because if the key had been null, this part would have been true, and this part wouldn't have got executed. So it must be that we're looking for a key that's not null, but we've come across a node in the tree which has a key that's null. So if the key in the tree is null, but we're looking for something that's not null, then we don't want to do this stuff. So we can just very safely and correctly put a guard in here and say, don't do this stuff if this.kv.key is equal to null. This.kv.key not equal to null, and that. Okay, so we can just say solve the bug that way. Let's see what happens now. So we shouldn't be doing that test if the key we're looking for is null. Let's see what happens now. Okay, we're failing, but we've still got another problem here. Okay, similar sort of problem. We're now doing hash code where the key is null. Where is that? Okay, if the this.kv.hashcode is null. Okay. Again, all right. So if the kv.key is null, then we want to go in the other direction. Okay. So if this.kv kv.key equals not equal to null, and those things. I thought I wrote that already. I'm confused. I thought I already did that somewhere, maybe somewhere else. Okay, so there. Okay, maybe I did it up here. Did I do that up here? I did. I did it up here. It's the same thing here. Okay, and I've done it down here now. Okay, so now let's run this. There's deja vu there. Okay, fantastic. So now we can put and we can put null, and they're both working. Now let's go to get, and to do get, we're going to use we're going to base it on the contains method because get and contains are analogous. Okay, so where's the contains code? That's pretty simple in the tree. So let's just take that code over, and hopefully it's going to be just as simple in the map, or more or less. All right. So let's go to a binary search tree map, and we'll go to the where are we? We've done the find. We've done the we're down here somewhere. Okay, we're doing get. All right, so we're going to drop that in there. So if the tree is equal to null and someone tries to get something from the tree, then we return null because that means the thing we're looking for can't possibly be there because the tree, there's an empty tree. Right, that's easy. Else, what we really want to do is we want to go and find from, we want to do a find of that key, which we did somewhere just up here, didn't we? Like this, all right? So now we're going to do the same sort of logic, pinch that code there. So that's going to find the parent, the node. Let's just not call that parent. That's a bit unpleasant. It should really just call it the node in the tree, right? It's the node in the tree. Okay, so now we're going to find the node in the tree that has the key, if there is one. If there's no node, we get null here, and again, we can just return null. If node, here, let's make this code simpler, make this a little bit more elegant. If the tree is not equal to null, and at the end here, we're going to return null. Okay, so if the tree is not equal to null, then we're going to go and find the thing, and if the node is not equal to null, then, oh, what's the matter here? What's the matter with this code? come on, IntelliJ, why are you complaining now? I just copy that code from there. There should be nothing wrong with this. I'm not sure what it's complaining about. All right, let's just keep forging ahead as if it didn't really complain. There's something unpleasant here that I'm not noticing. If anyone can see it, please yell, but I've just made a mistake here somewhere. Let's call this, change this to X and change that to X. No.
Hey Steve, you missed the bracket.
Oh, where's the bracket? Where? Oh, curly brace. A brace. I missed a brace. Okay, curly brace missing. Fantastic. Thanks, folks. I didn't see that. And it's annoying. IntelliJ didn't really point to that, but there we are. I guess it's ambiguous. It could have been either way. So, okay, so if it's not null, that means we actually found something. It means that we found the thing. So now what we're going to do is we're going to return the node.kv.value, okay? Because it means that if we did a find and the node was not null, it means this node has the value that we want. So we just return that. Otherwise, we return null. Okay, let's just run this test. Fantastic. We've now got that working. All right. Now let's see if we can do remove. Okay. Remove is a little bit more tricky. Let's give it a go. So BST map. Oops, wrong one. BST map. And we're going to try and remove this thing. Now, first of all, if the tree is not equal to null, okay, then we're going to need to break this down a bit because we now need to do a find again, okay? So, first of all, we see if the tree is not, we don't have anything to do if the tree is null, right? Then the next thing we do is say, same sort of thing we just did here. We're going to find the node in the tree that holds the key value, the key that we're looking for. Same thing. And then we write all the logic we're interested in here, okay? And at the end of all that stuff, basically this stuff, yeah, it's something like this. Okay. And again, I don't know why I call it parent. It's not really parent. It's actually the node in the tree, not the parent of the node. That actually confused me. So let's just call it BS tree like that. So, all right, so what we've done here, first of all, if we come to the tree and we're looking for this key and there's nothing in the tree, then clearly there's nothing to be done. So we just fall down to the bottom. Otherwise, we use our find method to look for any node in the tree whose key value pair is equal to the key we're looking for. And we return it here. Now, if that's null, again, there's nothing to be done. So we just fall down the bottom. If it's not null, then we do our stuff. And this stuff here is pinched directly from the set code. And first of all, let's go back to the PowerPoint so we can, so we can see what we're doing here. What we're going to do now, it's similar to the set code, is if we're going to remove, say we're going to remove pair. What we want to do is we want to delete this pointer. This pointer here, we want to get rid of it, okay? Get rid of that pointer there. And so orange no longer refers to pair because we're trying to get rid of pair and its key value pair. But we don't want to get rid of peach and plum. We don't want to get rid of them. But we do want the tree to have the correct structure. So what we're going to do is we're going to remember the peach. We're going to call peach L for left. We're going to call plum right, R for right. Okay, we're going to remember L and R. Then we're going to get rid of this. And then we're going to add left in, add right in. Okay, so let's go to that code. So there's our L. In that case, it would be peach, was it? Yeah. So peach is on the left. So that's now remembered the thing on the left, which is peach. That's remember the thing on the right, which is plum. Now, if we've got to remember the case where the node that we're looking at is actually the root of the whole tree, which is possible. So, for example, if we're removing apple, right? If we're removing apple, we're right at the very beginning. So that's a special case. We need to say if that equals the node, then we've got a null tree. Otherwise, we're going to go and remove the node. Okay? Killing the tree is equivalent of removing the node. Remember, the garbage collector will come and get rid of all the garbage later. So we either call remove node to if it's not the root of the tree. If it is the root of the tree, we simply make the root of the tree null. Okay, now we're going to put stuff back in. Now, if the tree is null, then we just make the tree equal to the left. Otherwise, we add left into the tree. Okay, and then the tree could still be null even if we just did that, because it's possible that both the tree is null and L is null, which means that the tree is still going to be null after that code's executed. So now what we need to do is we check if the tree is null. If the tree is null, then we just make the right-hand side be the new tree. Okay, otherwise we toss the right-hand side into the tree, which is like adding the Going back to here, it's like the right-hand side is plum. We put plum back into the top of the tree. Okay, and it'll find its own way, pair being excluded now. Okay, and I think we can get rid of all that code there. So let's get rid of that. It's just dead code now. Get rid of that. Okay, and the minus happens here. The minus only happens in this case here. So in tree, nothing in the tree. And here, okay. All right, let's give that a test. All right, and that's amazing. We've actually passed, but I just as I said that, my laptop, which I'm connecting to Leo on, died, so which is very sad. Ran out of battery. Look, folks, that's fantastic. What we've got here is we've just finished the map, and it worked. We've passed all of the tests, and right on cue, I've lost my connection to Leo. My laptop seems to have completely died. I guess the battery is completely low. So if you have any questions, it's super annoying because I can't hear your questions, which is a bummer. I'll try and revitalize my laptop while we finish this off. Let me try and recap now. What a sad time to die, because that was actually a very cool moment. We just finished and made the maps work. Let's just recap what we did. This section was about maps, and what I was trying to emphasize to you was the relationship between maps and trees. And sorry, I'm just restarting my laptop while we wait for Leo. I was trying to emphasize the relationship between maps and trees. Sets and trees. And so here we have sets and maps. I'm very distracted by the dying laptop. I'm sorry about that. Okay, so here we have sets, here we have maps. And we implemented the set two ways. We implemented in terms of a binary search tree. We implemented in terms of a hash. Okay, so we've got a binary search tree set. We've got a hash set. And then we went and did them in terms of maps. I illustrated that in the PowerPoint here by showing the relationship between the binary search tree set and the binary search tree map, and that they're actually remarkably similar. And that here we have elements in the tree, and here we have key value pairs in the tree. The key value pair being like Apple is the key, and $3.50 being the value. Okay, and then the same thing with the hash. We see that the hash set, whoops, where is it? The hash set looks like that, and then the hash map looks like this. And I'm still waiting for my laptop to come back to life here. Okay, all right. I'm going to go on to, what should I do here? My laptop should be back to life very soon, in which case I'd love to take questions on this, but I can't right now. Dang. All right, let me just one more time run through this to show you what we did with the code. Okay, so here's the binary search tree. Oops, let's get rid of that. Here's the binary search tree map. Remember that we added two inner classes. One was a key value pair, because instead of storing elements, we're storing key value pairs. The other thing I did was we added in a binary search tree as an inner class, and the binary search tree we got was based on the binary search tree we used for the set. And the two things are basically identical. What have we got here? Okay, look, my laptop's still dead, unfortunately. Very, very sad. I'm going to finish up here by going to our bio. Oops. Finish up with the bio. Today's bio is actually really cool, with a little bit of something for you to think about. The bio is Shafi Goldwasser, I can't say that properly, I'm sorry. Shafi Goldwasser, who won the Turing Award in 2012, but she also won the Gödel Prize twice. Remarkable achievements. She made significant contributions to what we call zero knowledge proofs. and to cryptography more broadly. Now I'm just going to spend a moment explaining to you what a zero knowledge proof is, or very, very roughly giving you an idea of what a zero knowledge proof is, because they're a cool concept and they're actually really important in security. And the basic idea is that there may be times when you want to communicate, you want to be able to tell someone that you know a secret without telling them what the secret is. Okay, so let's hear that again. You've got a secret. You want someone to believe you that you actually have the secret, and you want to prove to them that you have the secret, but you want to do so without telling them the secret. Okay? And that's a very powerful thing to be able to do. And it sounds kind of weird, but it's very, very important, because it means you can say, like I can say, I know how to open that door. I've got the secret that allows me to open that door. I'm not going to tell you what that secret is. You can't, but I can prove it to you what it is. And so let me show you an example of how this is done, an illustration of what how a zero knowledge proof might work. And this is a classic example. You can find this on Wikipedia if you want to have a look for zero knowledge proofs. And the basic idea is that Alice over here is in this weird cave with a secret door, and she tells Bob over there that she has the secret knowledge to open that door, but she won't tell Bob what that secret knowledge is, or allow Bob to watch her open the door. So what she does is she disappears into either A or B, and Bob doesn't know which way she went, right? So Bob doesn't know which way, whether she went to A or B, because if he did, she'd be revealing too much information. So what she does is she disappears into either A or B, and Bob says, I want you to come out at A. Okay? Now, obviously, if she'd happened to have gone on A, then she could do that without the information, right? But if she's on B, she needs her secret to be able to open the secret door to get to the A side. And the point is that if you repeated this multiple times, then Bob could gain very, very high confidence that Alice knew the secret without Alice revealing anything about the secret at all. Okay, so that might sound a bit weird, but this is a really, really important idea in security. And here's my laptop, still very sad. All right, I can show you a dead laptop. So unfortunately, I can't take any questions, because that's the way I take the questions. So I'm really sorry, folks. Sorry, I can't take any questions now. If necessary, I can follow up on Piazza. Otherwise, have a great week, and we're going to catch up on next Monday. There's no lecture on Friday. So have a great time, great week, and hit me up on Piazza if you have any burning questions I didn't answer. So again, apologies for that, and I'll see you